The presented method is based on Adagolojo et al. Automatic needle insertion method relying on an FEM simulation. They express the insertion as a minimization problem. The cost function is composed of objective functions chosen to follow a predefined path. Through a haptic interface, the proposed method allowed the practitioner to act on the decision-making part, the tip positioning target. He is provided with a virtual fixture to stay on the predefined path along with augmented visual feedback. What is important to note is that the user only controls the absolute position of the tip inside the tissue, and the base motion is computed by the automatic algorithm taking into account needle-tissue interaction. The proposed method allows the user to act on the needle tip target. The interface end effector motion moves the target following a local system of coordinates that moves with the tissue. A motion along the YZ plane moves the target away from the path. A motion along the X-axis moves the target along the path. Lateral virtual fixtures are provided to help the user to follow a predefined path. Virtual fixtures are spring-dumping-like forces close to the path and reach a maximum value far from it following a sigmoid. A second virtual fixture is provided along the X-axis. It is a damping evolving following a sigmoid depending on the actual violation of the objective functions. The lever is restored in the inverse simulation using only 2D informations of the internal marker coming from the C-arm. The internal markers are constrained following the projective line of the 2D points. The 3D position of the organ are then found thanks to its mechanical properties. Augmented C-arm images are provided to the practitioner along with the inverse simulation display. The restored path along with the tip target are displayed in an augmented view. The presented method is tested on a simulation of a real human body. The lever is moving constrained by a diaphragm motion on multiple tendons. A user study is conducted where the users need to place the needle tip inside a tumor located in the lever as precisely as possible. The method is compared to a fully automated method and a fully manual one. Here is a demonstration of a needle insertion performed using our method on the virtual patient. Thanks to both the inverse simulation and the visual feedback, the user is able to compensate for tip misplacement.